Hello everyone, and welcome back to some more remote learning. I'm the tutor in the Math Help Room, and today we're going to be doing some examples and practice of convergence of power series. Now, if you remember from my last example video when we did Taylor polynomials, I introduced the power series fairly quickly. So let's just go back over that one more time. A power series has the general form of c sub k times x minus a to the k, the summation of that from k equals 0 to infinity. And why we write it in this general form is that so you can see that this c sub k is just coefficients. So c sub k's are the coefficients of our power series, and a is where our power series is centered about. So a is the center of that power series. And if you thought about writing out a couple of terms, you can see that plugging in 0, we would just get c sub 0 times x minus a to the 0. So just c sub 0 times 1. Next, we would get c sub 1 times x minus a to the 1, so a first degree polynomial. Then we would get c sub 2 x minus a squared, a second degree polynomial, and so on. Now, if you recall in that last example video, we talked again about those Taylor polynomials. And if we take the limit as n approaches infinity of some Taylor polynomial, we have a specific type of power series, and that's known as the Taylor series, where if you remember in that video, our c sub k was the kth derivative of a all over k factorial, where this c sub k is our coefficient, but we're still centered around that a value. Now, before when we've talked about series, we've always cared whether they converged or diverged. But how do we tell that for a power series where now we have some variable x involved in there as well? Well, the convergence of a power series, there's going to be three basic forms of that. We're either going to converge at a single point, we're going to converge along an interval centered about that a, or we're going to converge for the entire real number line, so for all real numbers. And again, x is going to really dictate where we're converging at. So the set of x values for which the series converges is its interval of convergence. The distance from that center, which remember center is represented by a, so the distance from the center of that series to the boundary of that interval of convergence is known as its radius of convergence, and that's denoted by r. So for a power series centered at a, we said that we're going to have one of the following: either a single point, an interval centered at a, or the entire real line. So when our radius is equal to 0, if we're centered at a, let's try to draw this visually. If we're centered at a and our radius is 0, then we're only going to converge at that point. So we're only going to converge at x equals a. So that's our IOC, or our interval of convergence. IOC is x equals a. Now, when our radius of convergence is some finite number between 0 and infinity, our interval of convergence is between two real numbers. So, for example, if we're centered, looking at this visually, at a, and we know that we have some radius r, this point here is a plus r, and this over here would be a minus r, because remember, our radius swings both ways. So our interval of convergence in this case is going to be a minus r is going to be less than x, which is less than a plus r. And for this case, I'm going to make a note that we're going to have to test endpoints, because this could potentially be included in our interval. A minus r, we could potentially converge when x equals a minus r, and we could potentially converge when x equals a plus r. We just aren't sure. We know for a fact we're converging between those two values, we just don't know what happens at each of those values. So we're going to have to test the endpoints for this case. So let me go ahead and shade in the interval of convergence for this. So up above, we knew we only converged at that point, meaning when x isn't equal to a, anything else, we're diverging for this power series. In number 2, when we have some finite interval that we're converging for, everywhere outside of that, we're diverging. And that's where we need to test those endpoints to see whether we're converging or diverging at those. And then finally, we have when our radius is equal to infinity. And when our radius equals infinity, that means that our interval of convergence, if you imagine that radius swinging all the way towards infinity and then swinging back towards negative infinity, if we were to picture this visually, centering our power series at A, it's going to converge over the course of this entire number line. So for all real numbers, heading towards infinity to negative infinity. So in this case, our interval of convergence, which I'll label as IOC, is going to equal negative infinity to infinity. So x doesn't really matter what it is, we're always converging in the case of this power series. And I'll reiterate this at the end of the video. We'll go over this one more time after we go through some examples. But before we jump into those examples, we have to think about how do we necessarily find that interval of convergence? We've talked about the interval of convergence, but how do you find it? Well, for power series, we're going to either use the root test or the ratio test to determine the values of x for which our series converges. So again, we're either going to use the root test or we're going to use the ratio test. I have 3 examples planned out. You're going to see each of the cases above. For these examples, it says to determine the radius of convergence of the following power series, then test the endpoints to determine the interval of convergence. So if we're looking at A, let's go ahead and zoom in. We're going to decide our interval of convergence and our radius of convergence based on either the root test or the ratio test. So looking at this power series in A, I have everything raised to a k, so I'm going to start with the root test. Now, when I do the root test, I'm going to take the limit as k approaches infinity of the kth root, the absolute value of k times x minus 5, all raised to the k. And we're taking the kth root of the absolute value of what's in our series. And that absolute value is what's going to help us get that interval. So if I take the kth root of this, I'm going to have the limit as k approaches infinity of the absolute value of k times x minus 5. Now remember, I'm taking the limit as k approaches infinity. So here's where k is. This x minus 5, depending on what value I choose for x, is going to wind up being some constant within this limit. So I can pull my x minus 5 out in front. So for this, I have the absolute value of x minus 5, because that's the thing I don't know whether it's positive or negative, but I know that k is always going to be positive because we're plugging in positive values. So I'll leave the absolute value with x minus 5, and that's going to be times the limit as k goes to infinity of k. The limit as k approaches infinity of k, that's going to go towards infinity. So because we got infinity for that limit, what test did we do? We did the root test. So the root test tells us that our series converges when that limit is less than 1. So in this case, when is infinity ever less than 1? Well, it's not, except for when we're multiplying whatever k value we have by 0. So this is like case number 1 up above. We're only going to converge at a point. So we have to look at this and ask ourselves, what makes our limit get multiplied by 0? Well, that's when x minus 5 is equal to 0. So when does x minus 5 equal 0? That's when x is equal to a positive 5. So our radius of convergence in this case, our r, is equal to 0, and our interval of convergence, well, we're only converging when x is equal to a specific value, so that's converging at a point when x equals 5. And notice above when we said that r was equal to 0, we were going to converge only when x was equivalent to where it's centered at. Here you can see we're centered at an a value of 5, so there we go. x equals a. That's our interval of convergence. If I was to choose any other value for x, this series would diverge. For example, if I plugged in 6 minus 5 is 1, so then 1 times the limit as k approaches infinity of k, that's going to be infinity. Or if that was negative, taking that absolute value, we'd still go towards infinity. Let's continue on to our next example. In our next example, we have x plus 1 to the k all over 5 to the k. Again, we have everything raised to the k, so this is going to be a good case for doing the root test. So again, I'm going to label that I'm doing the root test when I'm finding my IOC and my radius of convergence r. The limit as k approaches infinity of the kth root of the absolute value of x plus 1 to the k all over 5 to the k, which is going to be equal to the limit as k approaches infinity of taking the kth root of my numerator, I get x plus 1, and taking the kth root of my denominator, I get 5. And remember, we're doing the absolute value of this. And notice that k is not involved anywhere in here. So our limit is going to be equal to the absolute value of x plus 1 all over 5. Because that 5 is always positive, I'll just put my absolute value around x plus 1. So if that's what our limit's equivalent to, remember we did the root test. And when does the root test tell us if our series converges? When that limit value is less than 1. So we just have to solve for when the absolute value of x plus 1 over 5 is less than 1. So we have x plus 1. I'm going to multiply both sides by 5. So when I do that, my 5 in my denominator gets canceled out, so I'll have x plus 1 is less than 5. So now finding that interval, so because this is the absolute value, that means x plus 1 is going to be either equal to positive 5 to get that furthest bound, or negative 5 to get that bound on the other end. So x plus 1 equals 5 when x is 4, and x plus 1 equals negative 5 when x is a negative 6. So negative 6 is going to be less than x, which is less than 4. Or an easier way to do this is to visualize we're centered about an a value of negative 1. So if we're centered about an a value of negative 1, here is our radius. We go 5 to the right, we get to a positive 4. We go 5 to the left, we get to a negative 6, because our radius, r, is going to be 5. Now, I know I'm converging between negative 6 and a positive 4, but I'm unsure of what's happening at those points. So this is the case where we check our endpoints. And how do we check our endpoints? Well, that's as simple as plugging in those boundaries and seeing what happens to the series by using any other test other than the one we just used to get the interval. So I'm not going to use the root test when figuring out if the series at my endpoint converges or diverges. So again, all I'm going to do is take that endpoint and plug it in for x in my series and see what happens at that value. So I have the summation from k equals 0 to infinity of negative 6 plus 1 to the k all over 5 to the k. Simplifying this down, that's going to be the summation from k equals 0 to infinity of negative 5 to the k over 5 to the k. But since both of those are raised to the k, I'm going to write this as negative 5 over 5 all raised to the k. And we know that negative 5 over 5 is a negative 1. So I have the summation from k equals 0 to infinity of negative 1 to the k. So this is the series I'm now testing. And again, I can use any of those tests we've previously learned for figuring out whether a series converges or diverges, as long as I don't go back and use the test that I used to get that interval. Because if I did use the root test on this, I'd get a value of 1 for my limit, which would be inconclusive. So redoing that test is just going to get something that's inconclusive. So I need to pick something else. Well, an easy one to do here is going to be the divergence test. Think about it. If I take the limit of -1 to the k as k goes towards infinity, that's never going to be equivalent to 0, because I'm going to have, if I'm starting at 0, that'll be +1, and then I'll be adding a -1, then a +1 to that, and then adding a -1, +1, -1, and so on. It's going to continue to oscillate for forever. So because of my divergence test, I don't get that the limit equals 0. I know for a fact it diverges. So because we diverge, we know that that endpoint, well, is it included in our interval of convergence? No, because we're diverging at that point, we're not including it in our interval of convergence. So I'm going to put an open circle around -6. And now we're going to test that other endpoint. We're going to test when x is equal to 4. And I'll go ahead and do this in a different color. Let's do this in light blue. So now I'm doing the summation of k equals 0 to infinity of, I'm going to plug in 4 for x, because we're trying to see when x is 4, does our series converge or diverge? So we have 4 plus 1 to the k over 5 to the k. Now this is going to give me the summation that k equals 0 to infinity of 5 to the k over 5 to the k, which 5 to the k over 5 to the k is going to be 1 to the k, or 1. So this is what our series is when x equals 4. Again, this is as simple as doing the divergence test, because if we do the divergence test and we take the limit as k approaches infinity of 1, which doesn't equal 0, therefore when x is 4, we're diverging as well. So because we're diverging when x is 4, that means we're not going to include 4 in our interval of convergence. So we're going to have an open circle around 4 as well. So now my radius we already determined was 5, and my interval of convergence, my IOC, is going to be -6 to 4. And notice that those are not square brackets, those are parentheses around that. You could also write this as -6 is less than x, which is less than 4. Either way of writing that is okay. So this was case number 2. Our radius was some finite value between 0 and infinity, and then we got some interval of convergence between 2 values. Notice that this -6 is what we were centered at, -1 minus our radius, so there's our a minus r, and then this 4, the upper bound, was our center plus our radius, a plus 5. So there you have, that was our a minus r, and here was our a plus r. And lastly, we're going to do the summation from k equals 0 of x minus 3 to the k over k plus 1 factorial. And since we've already done cases 1 and 2, and I told you that I was going to go over all 3 potential options for an interval of convergence, I guarantee you that this is going to be a radius of infinity. We're going to converge no matter what x value we have. So let's take a look at it. For this, we have a factorial, so that's a good cause to do the ratio test. Now the ratio test is taking the limit as k approaches infinity of a sub k plus 1 over a sub k. So if what's in the series is my a sub k, my a sub k plus 1 is going to be x minus 3 to the k plus 1 all over k plus 1 factorial. So now I'm going to take the limit of the absolute value of a sub k plus 1 over a sub k. But just to make this easier, as opposed to dividing by a fraction, I'm going to multiply by its reciprocal. So a sub k plus 1 is going to be x minus 3 to the k plus 1 all over k plus, and I'll go ahead and simplify down. This will be k plus 2 factorial, and I'll multiply that by the reciprocal of my a sub k. So that's going to be k plus 1 factorial all over x minus 3 to the k. Now, there's a lot of simplification we can do to get things to cancel out. I'm going to have the limit as k approaches infinity of the absolute value of x minus 3. I'm going to break this exponent apart and do x minus 3 to the k times x minus 3 to the 1, or x minus 3. And that's going to be all over k plus 2 factorial. But I'm going to rewrite k plus 2 factorial because k plus 2 factorial is larger than k plus 1 factorial. I know I'm going to be able to find k plus 1 factorial within that. So k plus 2 factorial, I'm going to rewrite as k plus 2 times, well, what's 1 less than k plus 2? That's going to be k plus 2 minus 1, which gives us k plus 1, and I could keep going, but instead I'm going to slap my factorial on here because k plus 1 factorial times k plus 2 is equal to k plus 2 factorial. And remember, that's all multiplied by k plus 1 factorial all over x minus 3 to the k. Now you can see why I rewrote this. My k plus 1 factorial cancels out with my k plus 1 factorial, and my x minus 3 to the k cancels out with this x minus 3 to the k. So it's going to leave me with the limit as k approaches infinity of the absolute value of x minus 3 all over k plus 2. So I move my absolute value up with my x minus 3 because I know that I'm only ever going to be plugging in positive values for k, so I know that denominator is always going to be positive. And now I can pull x minus 3 out in front of my limit. So the absolute value of x minus 3 times the limit as k approaches infinity of 1 over k plus 2, well, think about it. As k approaches infinity, 1 over k plus 2 is going to go to 0. And 0 times anything is 0. So I got that my limit was 0, and remember we did the ratio test. When do we know that we converge when doing the ratio test? That's when our limit, very similar to the root test, when that limit is less than 1. And 0 is always going to be less than 1. Therefore, I don't care what we're plugging in for x. X could be 100. 100 minus 3, that would give us 97. 97 times 0 is 0. Doesn't matter. So because we're always less than 1, this converges for whatever x value we plug in. So our radius is going to be infinity, and our interval of convergence is going to be from negative infinity to infinity. So real quickly, like I mentioned, let's go back up and review this one more time. Figuring out whether a power series converges or diverges, we'll use either the root test or the ratio test for these cases. So we're either going to get that our R value is equal to 0. So our radius of convergence is going to be 0, which means we're only going to converge at the center of our power series. So when x is equal to a. And let's make a note, if you remember, this was when our limit as k approached infinity of whatever we had, either doing the root test or the ratio test, that's when the limit equals infinity, then we're going to converge at a given point. Whereas in number 3, when we got that our radius was infinity, that was when the limit, doing either the root or ratio test, that was when that limit was equal to 0. Because 0 is always less than 1, it doesn't matter what our x values are when we plugged it in. And in this case, when we got that our radius was some finite value, that was when the limit as k approached infinity of whatever we had depended on x. So if you scroll back down, you can see that our limit was the absolute value of x plus 1 over 5. And depending on that x value, we'll get numbers greater than 1 or less than 1. So we had to solve for that interval where x plus 1, that absolute value, over 5 was always less than 1. So in that case of number 2, you'll get your limit to where it depends on x. Hopefully you found these examples helpful. Now, what I would say is to try to create power series on your own and then determine whether they converge or diverge. Try to create one that always converges. So that's when you do the root or ratio test and you get a limit that's equal to 0, because 0 is always less than 1. Or try to create a power series that only converges at that center value a. That's where you use the root or ratio test and you get a limit that's equal to infinity. And then the fun one to create is when you get that your radius of convergence is some finite value. So for x greater than something and less than something. And don't forget for those to check your endpoints. And if you need any help figuring out how to create those, your book has tons of examples, so take a look at that. So good luck and see you next video.